For the last topic of conversation in this section, we're going to investigate partial differential equations, or PDEs. Now, back in a previous calc class, hopefully you had a little bit of exposure to the concept of a differential equation, which is one in which both derivatives and functions find their way into an equation, and the goal is to ultimately solve for a function. So a partial differential equation is any differential equation involving partial derivatives. An example of a partial differential equation might be something like the second derivative of z with respect to x plus the second derivative of z with respect to y is equal to 0. This particular partial differential equation does have a special name. It's referred to as Laplace's equation. Now, there are lots of examples of differential equations. Basically, anything that you want to, or anytime you want to model something which changes based off of multiple variables, this would be a great way to do it. The heat equation is another example. The heat equation involves heat dispersion over the course of position as well as time. Laplace's equation has several different varieties of solutions. So first thing I'd like to do is show that z equals e to the x times the sine of y is a solution. Now, in order to do so, it means that we're going to need a couple of second partial derivatives, so we'll go ahead and evaluate those. So the first derivative of z with respect to x would be treating y as a constant and differentiating e to the x, which isn't going to do a whole lot. And same is going to hold true for the second derivative. Once again, the derivative of a constant times e to the x would just be that same constant times e to the x. Whereas if we were to differentiate with respect to y, we'll do one derivative at a time, that's treating e to the x as a constant and the sine of y as our variable, so that'll be constant times the cosine of x, or cosine of y. And then the second derivative, we would wind up getting a negative sine of y. Now you'll note that when we add these two derivatives together, we are going to wind up getting 0. So d squared z dx squared plus d squared z dy squared would be equal to e to the x times the sine of y plus the negative e to the x sine of y. Combining those together will give us 0. And this is not the only variety of solution of a differential equation that we could see. I would also like to show that z equals the natural log of x squared plus y squared is a solution. Now the derivatives are going to look a little bit different in this case, but we're going to go with it. So first off, partial derivative of z with respect to x is going to be, we'll employ the natural log rule as well as the chain rule. So that'll be 1 over x squared plus y squared times the partial derivative of the inside with respect to x. That'll be 2x. So we'll call that 2x over x squared plus y squared. The partial derivative with respect to y will essentially look identical, so we'll go ahead and shortcut that one. That'll be 2y over x squared plus y squared. Both of these are going to need the use of the quotient rule for our next derivative. So we'll start over here. D squared z over dx squared will be equal to, this will be low d high less high. And when I say d low would be the partial derivative with respect to x of x squared plus y squared, so that'll give another 2x. And this will all be over the square of what's below. Combining like terms that we see and distributing where appropriate, we're going to wind up with a 2x squared minus 4x squared. That'll be minus 2x squared plus 2y squared all over x squared plus y squared, quantity squared. We'll see something similar for the second derivative of z with respect to y. Once again, low, d high, that'll be the partial derivative with respect to y of 2y, less high, d low, partial derivative with respect to y will give us a 2y over the square of what's below. And when simplified completely, we'll wind up with 2x squared plus 2y squared minus 4y squared. That'll be minus 2y squared all over x squared plus y squared, quantity squared. Now to prove that it solves our differential equation, let's go ahead and set up d squared z dx squared plus d squared z dy squared. We'd like to show that this thing is equal to 0. We already have a common denominator for these two second partial derivatives. So really, I guess the only observation to make is that all of the terms in the numerators will cancel out. We have a negative 2x squared with a positive 2x squared and a positive 2y squared with a negative 2y squared, leaving us with 0. That solves our given differential equation.